A space station is constructed in the shape of a hollow ring of mass 5.65 times 10 to the 4th kilograms. Members of the crew walk on a deck formed by the inner surface of the outer cylindrical wall of the ring, with radius 150 meters. At rest, when constructed, the ring is set rotating about its axis so that the people inside experience an effective freefall acceleration equal to g. The rotation is achieved by firing two small rockets attached tangentially to opposite points on the rim of the ring. A. What angular momentum does the space station acquire? B. For what time interval must the rocket be fired if each exerts a thrust of 135 newtons? Okay, so part A of the problem asks us to find the angular momentum of the system. The angular momentum, which is L, is equal to I omega. And for a hollow cylinder, the moment of inertia is equal to 1/2 the mass times the first radius squared times the second radius squared. But in this scenario, the first radius is equal to the second radius because it's all uniform length. So we can simplify it r1 squared plus r2 squared to just 2r squared. And since there's a 1/2 in the front and a 2 there, they just cancel out. So the moment of inertia is just mr squared. And the angular velocity. So the problem states that the ring experiences a free fall acceleration equal to g. So using our equation, A is equal to r omega squared, we know that A is actually equal to g in this scenario. Doing some simple algebra yields omega is equal to the square root of g over r. So now that we know the moment of inertia and omega, we could solve for the angular momentum. Substituting our known values of 5.65 times 10 to the 4th kilograms for the mass, (150 meters for the radius), (9.8 newtons per kilogram for g), and again 150 meters for the radius. Plug this in your calculator yields an angular momentum of 3, 2, 4, 9, 3, 6, 4, 0, 7 kilogram times meter squared. So this is your answer to part A. Part B asks us how long the rockets have to fire to get the system from rest to having this angular velocity. So to do that, we're going to set up our torque equation. Except we're not going to set the net torque equal to I alpha like we usually do. We're going to set it to delta L, the change in angular momentum, over delta T, the change in time. This is similar to our calculus definition of torque, which is dL over dt, which implies the same thing, just when the differences are really, really small. So we know that there's going to be two net torques here. There's going to be one from this rocket pushing in this direction, and one from this rocket pushing in this direction. Now both torques here are going to be considered positive because they cause a counterclockwise rotation. So I wrote the net torque is equal to 2Fr because there's two rockets, both providing the same force, a given distance r from the center. And since it's starting from rest, we know that the total change in angular momentum is going to be what the current angular momentum is. We don't know delta t, that is what we're trying to find. So I'm going to do some simple algebra here and multiply through by delta t and then divide by 2Fr. So I know delta t is equal to our angular momentum that's a long number, divided by 2Fr. I'm going to substitute in our known values. The force that the rocket provides is 135 newtons. And again, the radius is just 150 meters. Plugging this all into your calculator yields 8,023 seconds. When I first solved this problem, I was confused with how to find the angular velocity. I could find the moment of inertia using the method described here, but I couldn't determine the angular velocity. All the problem gave me was that the ring experienced a free fall acceleration equal in magnitude to g. And I didn't know how to use that information to convert to an angular quantity. But then I realized we could use this fancy equation here, that acceleration is equal to r omega squared, and just substitute in g for a. This problem shows my growth as a physics student because it shows that I understand the concept of angular momentum and am able to quantify it. Also, it shows I still remember the concept of centripetal acceleration, which is acceleration towards the center. Lastly, this problem shows that I'm able to use a different definition of torque than just I alpha, which is dl over dt. Side note, while editing my video, I realized that the units I had for angular momentum were kilogram meters squared. That is incorrect. The correct units for angular momentum are kilogram meters squared per second. Thank you.